Good afternoon, everybody. We can start this third lecture of this course. Before going into the topic of today's lecture, last week we talked about measurement of period and frequency. And at the beginning of that topic, I said, well, frequency and period are one the opposite of the other. So you could measure the frequency and then recalculate the period of a signal. Or you could measure the period and recalculate the frequency. So why do we have two different methods to measure the frequency and the period? And I told you that there are some cases when you prefer to measure the period and some other cases when you prefer to measure the frequency. At the end of the lecture, after showing you these two different methods, I forgot to explain you when do you use the measurement of the method to measure the frequency and when, on the contrary, you measure the period of the signal. So I decided to leave it as an assignment for you. I added it to the MS Teams as a topic, so your task is to find out when you prefer to measure the period and when the frequency of a signal. Suggestion: look at the accuracy of the measurement. Okay? Try to look at how we defined the intrinsic accuracy of the measurement of period and the measurement of frequency. And then decide when one method applies better for one type of signal or for another type of signal. Okay? That's not so difficult, but try to find out and give me the answer. There will be, I guess, I put 1 point for that. It's not much, but it's a rather easy task. So I forgot to give the answer myself, and that became your assignment. If there is any question about previous lecture, just type it in MS Teams as usual, because I cannot see the comments on YouTube. Meanwhile, I make the lecture. Okay, if there is no other question, I will start with the lecture number 3. Today we will talk, yes, somebody's talking here. Who is talking? Maybe just a mistake. I cannot make your names, I cannot say your names publicly, so Mr. TT, you're active. Okay, no, now you're mute. Fine, let's continue. Measurement of RMS value and measurement of power and energy, which sounds quite strange. Why would we talk about these two topics together? RMS value and power, what do they have in common? Try to think about that. It won't be so difficult. We will see it in a while. Now, let's measure power. What is power? If I ask you how do you calculate the power in a circuit, most likely you will tell me that you have to multiply, sorry, you have to multiply the voltage and the current. So, if you have a very simple circuit like this, you have a DC generator of voltage, you apply it to a load, the load absorbs some current, and then you have a power which is defined by the product of the voltage and the current. I hope you don't hear the noise I'm hearing because, okay. No, I think something is going on, sorry. It's scary. Just a minor note. In this faculty, I will tell it for those who are studying here, not on exchange programs, but they are regular students of our faculty. I use this convention, okay? If I have a voltage drawn in this direction and the current drawn in this direction, I mean that the power is flowing from the generator to the load, okay? For some historical reason which is not very clear to me, in this faculty, almost everybody does the opposite. When they want to express the power flowing in this direction, they draw the voltage with the opposite sign. Now, it's a convention, so you can choose whatever you want. It's just important to be coherent. So if you use this convention in other courses, feel free to continue to use this convention even during the exam. Just write at the beginning of your exam that you are using this convention to define when the power goes in this direction, okay? That's up to you. But don't be confused. So always use the same convention, and when you have the voltage and the current with one direction, you mean that the power goes from the generator to the load, and if you reverse one, the power goes in the opposite direction. Fine. Now, when I ask to my students how to calculate the power, they know that the power is the energy over the time. In a circuit, here, if they define this surface, they know that the power entering and flowing through the surface is given by the voltage times the current. The question that I typically make to my students is, why? Why do you multiply voltage and current to get the power? Most likely students reply that, well, because they told me that's how you calculate it. Yes, but how is it related to energy over time? Now, I want to make a little survey. How many of you, without watching the next slide, would be able to answer? Just type me in the comment if you are confused about that. If you would be able to say why, if you want the power, you have to multiply the voltage times the current. Let's see if somebody is able to answer in the comment section of our streaming. That's quite tricky, because if you're silent, it means that you don't, or either you're ashamed to say it, or you don't know it, and I wait answers forever. So let's reverse the question. How many of you do not know it? Don't be shy. I promise I won't record your name. It's true there is some delay in YouTube, but okay, so I will give you directly the answer. What is 1 volt? What is the voltage? That is even an even trickier question. When I ask some student what is a voltage, typically they freak out. They say, that's the difference of potential. I say, yes, and what is a potential? And they cannot tell me this very basic definition. Voltage is the work necessary, 1 volt is the work necessary to move 1 coulomb of charge. You have a charge, an electric charge. Oh, somebody, at least explain me, said that she doesn't know it. You have a charge, and you want to move this charge from here to here. And you have to make some work to move the charge. Now, the larger is the charge, the larger is the work you have to do. If you want to move 1 coulomb, you have to make some work. If you want to move 2 columns, you have to apply twice the work. If you want to move 3 columns, you have to apply 3 times the work. If you take the work that you have to make to move a charge and you divide it by the amount of charge, you get the voltage. Okay? So you can say that the voltage is the quantity of work necessary to move a charge per unit of charge. So 1 volt is the work necessary to move 1 coulomb of charge. So voltage is the work divided by the charge, the unitary work per charge. If I ask what is the current, this is quite commonly a very easy question, because you remember the physics behind the current. The current is a stream of charges. So you have the charge streaming in a conductor, for instance, per unit of time. So the ampere is therefore a column of charge moving in 1 second. Now let's multiply them together. The voltage is the work that you have to make to move the charge divided by the charge. Then you multiply times the current, which is the charge over time, and you get what? The work over time. And the work over time is simply the power. Okay? Fine. So if we want to measure the power, what you have to do is to measure the voltage and the current. Here we go. We want to measure in this circuit. Let me draw again the circuit. You have the current here, and you want to measure this current, and you have a voltage, and you want to measure this voltage. How do you do it? You insert an ammeter where you want to measure the current, and you insert a voltmeter where you want to measure the voltage. You take your readings, you multiply current and voltage, and Bob's your uncle. You measure the power, right? And today's lecture is over. One topic is already solved. Now, we can have a break, go home, have a coffee, and bye-bye, right? No. Unfortunately, it doesn't work like that. It's not so simple. Why? Well, first of all, we do not have ideal ammeter and voltmeter. Any instrument has a resistance, as an input resistance. It depends how it's built, but generally speaking, it will always have an input resistance. In this case, we are talking about DC power, so I'm talking about resistance. Generally speaking, they have an input impedance. So instead of drawing in our schematic an ammeter and a voltmeter, we replace them with the resistances RV, which is the input resistance of the voltmeter, and the resistance RI, which is the input resistance of the ammeter. And you say, okay, and what's the problem about that? Well, the problem is very easy to spot. Now, look at the voltage. Look at the voltages in the circuit. You want to measure V load, which is the voltage applied to the load. And that is exactly what the voltmeter measures, right? Vm, the voltage that you measure, is exactly equal to the voltage on the load. And that's fine, no problem whatsoever. But what happens when you want to measure the current? You measure the current Im. That's the current flowing through the ammeter. In this case, you have the Ri instead of the ammeter. Okay? But that's not the current which flows into the load. The current which flows through the load is I load, which is different than Im, the current that you measure. Why? Because there is a current which flows through the voltmeter, IV. So as a matter of fact, you want I load, which is the current in the load, but you measure Im, which is slightly larger. Somebody's talking? Any question? Mr. VF, I see that you're talking. Okay, maybe he just forgot his microphone. Yes. Okay. So, what we have to do now? I want I load. So, in the calculation of the power, I cannot use... Okay, so again, somebody's talking. Okay, Mr. VF, I'm not sure if you are talking because you want to make a question or you are talking because you forgot your mic on. Let me... Okay. Fine, sorry. I apologize if there are these pauses, but I have to take care also about the MS Teams section. So when you calculate the power, you want I load, which means that you take IM, the measured current, and you subtract the current in the voltmeter IV. How do you know this value? Well, you take the measured voltage, VM, and you divide it by the value RV, the resistance of the voltmeter. The input resistance of the voltmeter, it's something you typically know. It's a parameter of the voltmeter. You can watch it in the data sheet of the voltmeter. So you can make an estimation of the current in the voltmeter without measuring directly the current in the voltmeter. It's just enough the reading of the voltmeter itself in volts. You know the resistance of the voltmeter, you divide it and bob's your uncle. You get the current. So when you measure the voltage with the voltmeter, you automatically know also the current flowing through the voltmeter. Okay? And here we make a correction of this error. It's a methodical error, which means that it's an error given by the method we are using to measure the power. It's not something random. We can estimate it. And therefore, we can correct it. If you remember the lecture, last week lecture about uncertainty, I told you that when you talk to somebody who is working metrology, you should never mention the word error of measurement. Because most of the times, what you refer to is not an error, it's uncertainty, which is a different thing. So when metrologists, which are really, really weird people, trust me, when metrologists hear the word error, they start burning, getting red, and they probably would like to choke you. In this case, you can use the word error. This is not uncertainty. This is really error. Why is it an error? Because it's something you can estimate and correct. You can estimate because you know how large is the current flowing through the voltmeter. Therefore, you can calculate it and you can subtract it from the measurement of the current that you obtained using the ammeter. Okay? Of course, your estimation will not be perfect. That's fine. But it's not something that is within a range. It's a value that you can calculate. You can calculate it and you can subtract it. So it's an error that you can correct. You know it. If you remember when I started talking about the uncertainty of measurement, I said that the old style approach, that one that gave a measurement with the measured value and the error, was not valid because you don't know the error. If you knew the error and you measure the value, then it means that you also know the true value of the measurement. And that is not true. You never know the true value of the measurement. That's why we moved to the new style approach of the uncertainty. In this case, this particular error is something that you can estimate, right? And therefore you can correct, and therefore it is an error and not an uncertainty. Fine. So if we have this problem, somebody might propose, why don't we move the voltmeter before the ammeter, right? In this case, with this other schematic, we have the voltmeter here before the ammeter. The current flowing through the ammeter is the same current which flows through the load. That's the very same current. Therefore, we don't have this difference between the current in the load and the current measured by the ammeter. Fine, everybody's happy, we solved our problem, we can go home. Well, you actually are already at home. May I go home? No. Why? Because again we have the opposite problem. It is true, the current which flows through the load is the current which flows through the ammeter. That's the very same, they are in series. But now the problem is on the voltage. The problem now is that despite you measure the true current flowing through the load, the voltage now is not, the voltage that you measure is not the same voltage that you have on the load. In this case, the voltage that you measure, Vm, is the sum of the voltage on the load plus the voltage on the ammeter, Va. And therefore, again, you have to apply a methodical, a correction of the methodical error, which means that when you calculate the power, you have the V load times the current on the load, and you calculate the voltage on the load as the difference between the voltage that you measure and the voltage on the ammeter. And again, if you want the voltage on the ammeter, it's enough to multiply the reading of the ammeter, the current, times the resistance of the ammeter, which is a parameter of the instrument. Fine. So now you understand why, in an ideal world, the ammeter has zero input resistance. It's a short circuit, right? Why? Because if you have a short circuit instead of an ammeter, basically you don't have any voltage drop on the ammeter, which would make the reading of the voltmeter different than the voltage on the load. Okay? If you watch the previous graph here, if you have an ammeter which has zero resistance Ri, then the voltage that you measure, Vm, is equal to V load. So there is no error whatsoever. In the very same way, if you have a voltmeter which has an infinite input resistance, there is no current IV which flows through the resistance of the voltmeter. Therefore, the measured current Im is equal to the current which flows through the load. So, basic rule, in an ideal world, the ammeter is a short circuit. All the current can flow through the ammeter without having a voltage drop on the ammeter. It's a short circuit, it's perfect. All the current flows through and there is no voltage drop on that. Perfect. It's like if it's not even there. It's like a wire, an ideal wire instead of the ammeter. Okay? And the voltmeter has an infinite input resistance, so infinite that it's like if you don't have a voltmeter there. It's like if you have nothing. And what does it correspond to if you have nothing between 2 points at different potential? Open circuit. Open circuit means infinite input resistance, okay? Fine. So this is very important. Always keep it in mind. Ideal ammeter short circuit. Ideal voltmeter is infinite, it's open circuit. You should remember this concept as your own name and the date of birth of your mother. Because if you forget it, that's bad, okay? I will tell you what happens when you forget this basic concept. Typically, in our course, we have also a practical exam. Unfortunately, we cannot do it now because we cannot meet in person. Nevertheless, typically we have this practical exam. We give something like 10 points for the practical exam. And the student had to measure the, I think, the power absorbed by an LED. So he had his own nice generator. He knew he had to measure some current. And he put an ammeter here. And then he had the LED whatsoever. Now, unfortunately, he didn't wait for me before turning the generator on. He did it himself and he was surprised that nothing was working. Why? Because an ammeter is equivalent to have a short circuit, right? Well, of course, it will not be ideal, it will not be zero, it will be very low, the resistance. But it's almost like a short circuit. And what was he doing now? Here, instead of the ammeter, he had a short circuit, and he was shorting the generator. Lucky enough, the ammeter had a fuse, so basically the result was that the fuse blown, and we had to replace the fuse, which cost, I don't know, 1 crown, 2 crowns. It was not such a big loss. We replaced the fuse, and that was all. But if you are not so lucky, you can blow up your ammeter. Okay. So always remember this basic fact. When you are inserting in a circuit an ammeter, you are inserting a short circuit. In ideal voltmeter, it's an open circuit. Okay, fine. Always keep this concept in mind. What about AC power? AC power, I'm not sure if you are familiar with AC systems. In this case, we have voltage and current on a resistor. You have a sine wave of voltage, you apply to a resistor, and you get a sine wave of current. The principle is the same. The principle is always that the power is given by the voltage times the current. Which means that now that we have a sine wave, we have to multiply the current times the voltage, and the power is always, at every instant of time, the voltage given by the voltage times the current. If you multiply the voltage here, sine wave, times the current, you get this instantaneous power. Okay? You shouldn't be surprised to see that the power has a frequency which is twice the frequency of the current and the voltage. In this case, you have 50 Hertz, surprisingly, because in this country we use 50 Hertz. In other countries, they use 60 Hertz. Here we have 50. And what happens when you multiply two sines at 50 Hertz? Generally speaking, what happens when you multiply two sines at different frequencies? In the output, you will have, as you remember from last lectures, or if you remember from trigonometry lectures, the sum and the difference of the two frequencies. The sum is clear. If you have 50 and 50 Hertz, the output will be 100 Hertz. And here you see it, because you have, if you watch here, the period, instead of being 20 milliseconds, the voltage and the current have a period of 20 milliseconds. Here, for the power, the period is only 10 milliseconds. So it means that in 20 milliseconds, you have twice the same period, right? So now the frequency is twice 100 Hertz. And what is the difference of the frequency? Well, 50 Hertz minus 50 Hertz is 0. And what is 0 Hertz? It's a DC value. DC value, by definition, is something that it doesn't change in time. So it's constant. That's DC component. If you're still confused, check the sign of this waveform. Now we have voltage which is positive, current which is positive, and of course the resulting power is positive. What happens when you have negative voltage and negative current? You multiply the voltage, which is negative, times the current, which is negative, and again you get positive power. On a load, this would be having the power going in this direction when you have the voltage and the current in this direction. right? And of course, now I have sine. When you have your load and the current is reversed and the voltage is reversed, then you reverse both. So the power still goes in the same direction. And if you have problems to see it, the current here, you can follow the current and see that you are doing the very same thing. Okay? So again, the power is going in this direction. If you want to reverse the sign of the power, you must reverse either the voltage or the current. If you reverse both, it's like the power goes still in the same direction. The power that you have on the load is the average of this instantaneous power. Okay? At the end of the day, the power that you transfer. Question. Let me finish here. So, if you calculated the total amount of power that you transfer in a given time, so you calculate the power, which is the work that you transferred in a given time divided by the time, it means that you have the average of the instantaneous power over that period of time, which means that you take the average of the voltage times the current in that time, which corresponds to the average of the instantaneous power. Now, let me read the question. Yeah, Mr. BD, that's exactly the point that I'm going now. So he's asking, so if the current was shifted half a period, then the power would change values between positive and negative in the graph, and that's exactly what we are going through now. What happens if the current is shifted of pi half? Now here you wrote half a period. Maybe you meant quarter of period. Not sure. Let me finish and then maybe you can rephrase your question. What happens if the current is shifted by pi half? Okay? This happens if your load is either capacitive or inductive. You have a shift of the current which is plus minus pi half. Here we can make again the same trick. We can multiply current and voltage and see what you obtain. Here you have the current which is positive and the voltage which is negative. You multiply them and you get negative. Then in the second quarter of the period you have both the current and the voltage positive. The result therefore is positive. Then you have the voltage which is positive and the current is negative. The product is negative. And then finally you have both the current and the voltage which are both negative, and therefore the product will be positive. Again, you have the sum and the difference of the two frequencies, in this case 50 Hz. The sum is 100 Hz, and again you have 100 Hz in the output. You see that the period is again 10 milliseconds, therefore the frequency is 100 Hz. Yeah, so meanwhile your colleagues say that that's what he meant. But, so you still have 100 Hz. And what about the difference of these two frequencies? The DC value now is 0. Compared to this situation where you have the 100 Hz and you have the average here at 1, now you have the same AC, the same 100 Hz component. Here the 100 Hz component was between 0 and 2, with an average therefore of 1. And here the average is 0. You still have the same component, which is between -1 and 1, and not between 0 and 2. And you shift down the average to 0. What does it mean from the physical point of view? Here, I will explain it here. It means that for a quarter of a period, when the current and the voltage are with the same polarity, plus, plus, then you get the power which moves from the voltage generator to the load. So the current goes from the left side to the right side. When only one sign is reversed, either the voltage or the current, the product is negative. You multiply voltage and current, one of them is negative, and therefore the energy, the power is reversed. It means that the energy returns back. So for every quarter of period, you have the energy, an amount of energy which goes there, and in the next quarter of period, the energy returns back. At the end of the day, there is no net transfer of energy. The same energy goes there and then returns back. So when you calculate the average at the end, you have no net transfer of energy. That is what happens when you have an inductive or capacitive load. For instance, with a capacitor, you put energy in the capacitor and then you get the energy back. You do not convert it into heat, into work, into anything else. It's like a bucket of energy. A capacitor, you can see it like a bucket of energy where you put the energy in and you get the energy out. The same for an inductor. For an inductor, the energy is stored in a magnetic way instead of in an electric field. Fine? But it's a storage of energy, both the capacitor and the inductor. You put the energy in and you get it out. So there is no net transfer of energy. Generally speaking, you can have a phase which is non-zero or pi half. It's a general phase phi. And if you have a general phase phi, you can have a situation in the middle between these two extreme cases where you still have your 100 Hz component and the average is given, the average power is given by the voltage, RMS voltage, times RMS current times the cosine of that angle phi. So if phi is 0, like in this case, there is no phase difference between voltage and current, you get cosine of phi, cosine of 0, which is 1. Okay, so the voltage, the power is simply the voltage times the current. If you have pi half, the cosine is 0, and therefore you get no net transfer of energy. Therefore, the average of the power will be 0. Cosine of pi half is 0, clearly. Why did I talk about all this topic before getting to the methods to measure the power? Because in AC systems, you need also to measure the reactive power. Reactive power is that power that you continuously transfer to the load and get back from the load at every quarter of period. It's not a power which is transferred. It's not an energy which is transferred to the load. So it's not something that you can bill to your customer. If you are a company selling energy, you sell energy, which means that the power that you transfer to your customer and which keeps there at the customer forever. He can use it to warm up the office, he can use it to create light, he can use it to make this system work and transmit you these images. He can use the power to move electrical machines, motors, welding stations, whatever. It makes them work. You sell energy. Therefore, you can bill it. to the customer. But the reactive power is not creating any work. I don't use it to generate heat or light or movement on my electrical machines. So I take something, but then I return it back to you. It's like with Amazon, right? You buy something on Amazon, and then you return it back. And then you order it again. And then you return the same item back again. At the end of the day, Amazon cannot bill you for that product because you are not keeping it. You're returning it. Unless maybe they can charge you the shipping fee. Unless you have some special offer. Because they have to make some work to bring you that item. And that's not fair that you return it back and you don't pay anything for the shipping fee, right? The very same thing applies for electrical energy. Why we want to measure the reactive power, this energy that is transferred to the customer and then received back? Because it's true that it doesn't stay there at the end of the day at the customer place. But I have to bring it to you. And that means that I have to, I have some expenses to do it. The electrical energy doesn't fly on the power of magic. Okay? If I have here my power plant, and here I have my factory. So this is the factory. And this is the power plant. I have to transfer the energy from the power plant to the factory, which means that you have transformers, you have cables. Now, I will not draw everything, but generally speaking, here I have some electric lines, right? You have transformers, which have losses. You have transmission lines, which have losses. And they must be built. So if I transfer only active power, I will build some transformers, lines, and whatever of one dimension. If I have also reactive power, which every 5 milliseconds goes there and return back, then I have to build bigger cables because I don't have only the active power, but also the reactive power which flows on the cables. It doesn't stay here, but still you have to build an infrastructure to let this queue run back and forth, which means that you have bigger cables and you have bigger losses because on the net you will have some current which flows. Sure, it flows in one direction and returns back. But meanwhile it flows and it will generate some losses on the highway, let's say. This is mainly a concern if you want, if you are talking about an industrial system. In our domestic electric systems, this is basically negligible. You can forget about this type of losses. In industrial systems where you have large motors, large electrical machines, and therefore large inductive loads, that is a problem. The electrical companies do not want you to have Q, because otherwise they should have larger electric lines. So, if you have here an electrical machine which has an inductive behavior, the company forces you to put here some capacitor in such a way that the inductive component of the electrical machine will ping-pong this reactive power between the machine and the capacitor, okay? So instead of traveling over the transmission line, the reactive power will just travel within the company, within the electric system of the company. So here you will have only the active power flowing through the network, and therefore you don't have to create such large transmission lines, okay? That's why it is true that you cannot charge Q, because it's not a net transfer of energy. But the companies selling you energy, they can force you to have a very small or very large, very small phase. In this case, so typically they say that the cosine of phi must be larger than 0.9, okay? So they cannot force you to have cosine of phi equal to 1. That's unrealistic. But at least they tell you, you should put here a capacitor so that the quantity of the reactive power flowing through the system, through the transmission line, is slow. How much? Well, if you have a cos phi of 0.9, of 0.7, for instance, you should put here some capacitor and bring it up so that it will be larger than 0.9. Okay, they cannot ask you 1, but at least they can ask you more than 0.9. And that's why you need to measure also Q. It's not enough when you have a measurement system at a factory. It's not enough to measure P. You have the active power. It's also necessary to measure the reactive power, Q, okay? Which is, of course, given by the voltage, RMS value, the current, RMS value, times the sine of phi. So you can see it as a triangle. You have the active power, which is the voltage times the current, times the cosine of phi. And then you have Q, the reactive power, which is given by the voltage times the current times the sine. What happens if you reduce Q, the reactive power? So this is P, which is the voltage, current. I don't write RMS because now you understand, cos phi. And this is Q. Q1 or Q2. Now, Q will be voltage, current, sin phi, okay? What happens if instead of having Q2, I reduce it? I reduce the angle phi so that I have less Q in the system. This vector, S, which is V times I, for the same voltage has a lower current. You see that the length of the vector now is lower. Therefore, it means that the current decreases. For the same power, active power, you transfer the same amount of energy, which will then be used to create work in the factory, and on the line you will have less current, which means that you have smaller cables, cables with lower diameter, lower transformers, a lower power transformer, and so on. Okay? That's why when you design these electrical machines, when you design transformer, you watch which is the rating. And you see that it's expressed in volts ampere because they want to know which is the current we can transfer. Then, of course, there is the case of non-harmonic waveform, but it's out of the purpose of this course. How do we measure now the power in AC electric systems? The principle is the same. You have to measure the current and the voltage. But this is not enough, because we have to take into account also the phase. If you want to measure the active power, you have to measure the voltage, the current, and the phase between them. Because the active power will be proportional to the cosine of the phase. And how do you do it? It's not enough to have two instruments, independent, voltmeter and ammeter. You need a wattmeter. Because you should measure both. You should measure both the current and the voltage simultaneously in such a way that you take into account also the phase between them. Quite commonly, you have also an ammeter here to check that you don't saturate the current, the current range of the wattmeter. Now, be careful. When you use a wattmeter, which is a voltmeter plus an ammeter, you have four terminals. You have here terminal for the current, 1 and 2, and the terminal for the voltages, 1 and 2. So you have two couples of terminals for the current and the voltage. Each of them has a sign, which refer to the sign that we have here, right? Let me change. So we say that if the power goes in this direction, you have the voltage, which is considered positive in this direction, and the current, which goes into this direction, okay? So if you have here an ammeter instead of the current should enter here. So we have on the wattmeter a mark, a symbol, which tells us that this is the entrance for the current if you want to consider this current to be positive. In the very same way, for the voltmetric part, you will have a marker which tells you this is a symbol telling you that the sign of the voltage is considered positive in this direction, okay? With the voltage pointing like this. That's why when you watch at the wattmeter, you should always be careful to the sign of the two pairs of inputs, okay? And be also careful because both the part of the wattmeter which measures the current and the part of the wattmeter which measures the voltage could be saturated. But then you don't see the instrument giving you a saturated value. Why? Because maybe the current is saturated, but the voltage is not saturated, it's much less. So when you multiply them, one is saturated, the other is way below the maximum range, and when you multiply them, you get something which is way below the total power of the which can be measured by the instrument. That means that you don't realize that the instrument is saturated because you don't see overload on the wattmeter, because the total power is still less than the total power the instrument can measure. But in the background, one of the two parts, of one of the two components of the wattmeter, for instance, the one which measures the current, is saturated. Okay? So it's always wise to have also an ammeter in series to measure the current. We still have the same problem. We have to apply the correction of the methodical error, the very same thing we did before with the DC measurement of power. In this case, it's better to use this right-hand side schematics because the power of absorbed by the current side of the wattmeter is typically lower than the power absorbed by the voltmeter component of the wattmeter. Fine. So all the topics about, all the discussion we made before about the correction of the methodical error for the measurement of the power is the very same here. Nothing changed. Now, we want to measure the reactive power, okay? We said that we have to move from the cosine to the sine. The active power is given by the voltage times the current times the cosine of the angle between these two, voltage and current. The reactive power is given by the same voltage, the same current, but the sine of the angle. How can we do it? We need to shift the measurement by pi half. We need to shift one of the two components by pi half. In this symbolic drawing, I put a block which shifts pi half, by, which shifts the voltage by pi half. We still use a wattmeter. We don't use a var meter. The instrument is still the same. From the physical point of view, it's still measuring the active power. But we put a shift on the voltage so that it will measure the, in reality, the reactive power. Okay? From the physical point of view, it still measures the active power. But it measures the active power with the voltage shifted by pi half. And therefore, if you shift the voltage by pi half, what is cosine becomes sine. How do you do it? And now, let's see if you have any suggestion. How do you achieve this shift of pi half? Give me some suggestion in the chat of the MS Teams. Let's see if you have any idea. I'm not sure which is the background of the exchange students, so I don't know if they are expert in this field or not. Let's see if there is any comment. Any idea? I can see also the comments here, actually. That is the bad part of teaching without people directly in the room. Because at least I would see if you start watching somewhere else. No idea suggested, but inductive coil would do the job. Oh, somebody suggests to use an inductive coil. There are even circuits which can introduce phase shift. There are some electronic circuits which you can use to introduce a phase shift. There are a lot of systems, but actually it's not necessary. Why? Because I told you that this kind of measurements are typically performed on industrial systems. And you probably know that in an industrial system, you don't use a single phase power supply. You use a three-phase industrial system of voltages. Okay? What does it mean? It means that you have not a single voltage, V1, which is a sine wave, but you have three voltages, V1, V2, and V3, of the same amplitude, and shifted by 2/3 of pi. Okay? In a phasor diagram, you will have V1, V2, and V3 in this arrangement. And the phase between them is 2/3 of pi. It means that at your factory, you will have three lines, L1, L2, and L3, and eventually a neutral. The load typically is composed by three-phase load. Okay? A motor, an electric motor, typical load in a factory, is composed by three phases connected to the three voltages of the system. Now, What happens, for instance, if you have a perfectly balanced load? You have a symmetrical voltage system, which means that the voltages have the same amplitude and they are perfectly shifted by 2/3 of pi. And then the load is the same. So for instance, if you have a motor, all the phases of the motor are equal. So every phase absorbs the same current. I1, I2, I3 in amplitude are the same. Of course, the phasors are different because they are shifted by pi half, by 2/3 of pi, sorry. The phases are the same. So if you want to measure the power absorbed by the load, in this case a motor, it's enough to measure the phase, it's enough to measure the power of one phase. For instance, the phase 1, we measure the current I1, which enters in the first phase, and the voltage between L1 and neutron, which means that it's this voltage between the line 1 and the neutron. And then we simply multiply times 3 the power that we measure. Fine. All the phases are equal. All of them receive the same current and the same voltage. You measure the power on one line, and then you get multiply times 3, and Bob's your uncle. What happens if you want to measure the reactive power? You want to measure the current which enters in the line 1, but then you don't want V1, because then the Voltmeter would measure, as here, the reactive power, the active power. We want a shift of the voltage by pi half. How do we achieve it? Well, let's just look at this diagram. If you watch carefully, you have already a voltage, I promise it's not COVID, at least I hope. And even if it's COVID, you are not in front of me, so there is no danger for you. You have already, in the diagram, 2 points which give you a voltage orthogonal to V1. You remember, we have to introduce a voltage shift of pi half. So pi half means that we need to create a 90 degrees shift. So it means we need a voltage orthogonal to V1. And where is the voltage orthogonal to V1? Is here, between the line 2 and 3. If you take the voltage between the line 2 and line 3, you get a vector V23, which is the vector joining the point 2 here and the point 3 here. And this voltage, as you see, is orthogonal to V1, right? So I still connect the Voltmeter in the same position when it comes to the current. So it will measure still I1, but then it will not measure the voltage V1, but a voltage V23, which is orthogonal to V1, which means that it will be shifted by pi half. And that's why the voltmetric connections of V1 are connected to the line 2 and 3. Okay? Just give me 1 second. I have to mute here. So. I apologize. And now we can continue our lecture. Okay, I hope I will not sneeze anymore. Fine. So here, the voltage terminal of the wattmeter are connected between the line L2 and L3. And therefore, we get a voltage V23, which is orthogonal to V1. Fine. So we don't actually need to take V1 and shift it by pi half. It's just enough to take V23, which, thanks God, is already shifted by pi half. Okay? What's the problem? The problem is that V23 is bigger than V1. The amplitude of V23 is square root of 3 times bigger than V1. Therefore, the power that you achieve measuring the reactive power with this configuration will be square root of 3 times bigger than the actual reactive power. So, in this case, we have all three phases together equal. We measure the reactive power on the phase 1. We use V23 for the voltage. So we have again a wattmeter, which measures, on the contrary, the reactive power, because we used a voltage which is shifted by pi half. But the number that we achieve is square root of 3 bigger. So for the total power of all three phases, we have to take the measured power PM, which is given by the wattmeter. We have to multiply it times 3. But then we must remember that we must divide this value by the square root of 3, right? Because the voltage is square root of 3 times bigger than V1. So as you see, you don't need any circuit to make the phase shift of pi half. It's already there in the system. Just you have to notice that you have a voltage shifted by pi half already in the system, which is V23. What if you have an unbalanced load? The voltage is still symmetrical, but the current is different. In this example, I have the first phase which absorbs I1, very large, with low phase V1. The phase number 2, which has a current of a lower amplitude and bigger phase. And then I3, which has an intermediate current and a very small phase. Okay? Now, in this case, you cannot just measure, as we did before, one phase and then multiply time, one power absorbed by one phase and multiply it times 3. Now we have to measure the individual powers. In this case, for instance, if we have 4 wires method, so we have also the neutron, we must notice that the sum of the currents, I1 plus I2 plus I3 plus the current in the neutron, is 0. Therefore, we can measure simply the current, the power in this way. We put 1 wattmeter for each phase. We have the current I1, current I2, current I3, voltage V1, V2, V3. We multiply, or better, the wattmeter multiplies them for us, giving the 3 individual powers, and Bob's your uncle, you get the total power. What happens if you don't have the neutron? In this case, the sum of the 3 currents will be 0, because you have no current in the neutron. In this case, you need only 2 wattmeters and not 3 wattmeters to measure the power. Why? Actually here. You can use this connection. You put a wattmeter on the first line, which measures V1, and the voltage is between the third line and the first line. So you measure V13. You don't have access to the neutron. It happens sometimes. So you cannot put the wattmeter with the second terminal here at the neutron. You have to connect it to the third line. The same for the second wattmeter. It measures I2 and then the voltage V23. What happens when you sum up these two readings? Well, in this case, as I told you before, the power will be given by the average of the voltage times the current in all three phases. So V1 times I1, V2 times I2, V3 times I3. But you remember that the sum of the three currents must be 0. So instead of I3, I can plug I1 plus I2 negative. Why? Because I3 is equal to negative I1 plus I2. So, and what happens if I connect here, sorry, negative I1 plus I2 times V3? If you arrange these terms, you find out that you have V13 times I1 plus V23 times I2, which is actually what we are measuring. Here, this is the power measured by the first wattmeter. You have the current I1, and the first wattmeter measures the current I1, and you measure the voltage 13. And that's exactly what you're measuring here, voltage 13. The same applies for the second wattmeter. You measure the current I2, here we go, and the voltage V23, which is exactly what you measure by plugging the wattmeter with this configuration, right? So, by putting these wattmeters in this configuration, you measure the sum of the three powers, okay? Fine. What happens when you want to measure the reactive power? The principle is the same. You have to measure the individual reactive power on all phases, and you do it by always looking for a voltage which is orthogonal to the voltage of the phase you want to consider, okay? So, in this case, the first wattmeter is connected, as we have seen before, between the terminals 2 and 3 to find the voltage orthogonal to V1. What about the other wattmeters? The second wattmeter measures the current I2, and then it measures the voltage V31. Why? For the first wattmeter, we have already seen it before, how it works. For the second wattmeter, we are considering the voltage V2, which is this vector here. And we need a shift of pi half. So, we connect the voltmeter between, or the voltmetric part of the wattmeter, to be precise, between the terminal V3, between the terminal 3 and 1. Okay? Be careful. It's pointing with the arrow to the point to the line number 3. Don't switch it, okay? Otherwise you get negative power. So, you measure here, you connect the terminal of the wattmeter between the point number 3 and the point number 1, okay? Therefore, your voltage will be V31, which is orthogonal to V2. And again, you have to remember that the reactive power is obtained by dividing the reading by the square root of 3, okay? Because the voltage is bigger, it is square root of 3 bigger than V2, okay? The same for the third line. So you have the current which enters in the wattmeter. You have, therefore, you want a voltage which is orthogonal to the voltage V3. And where do I find it? I find it between the points 1 and 2. Okay? So you connect the terminals at the point 1 and the point 2, which is which gives you a voltage orthogonal to V3. And again, remember that you have to divide by the square root of 3. This is kind of natural. Students kind of always remember to connect the wattmeter in this configuration. In any case, you have to select always the two other lines. If you measure the current on the line 3, you have to connect the voltmeter on the line 2 and 1. If you measure the current 2, you have to put the connectors of the voltmetric part of the wattmeter on the line 1 and line 3. If you measure current 1, again, you have to find the voltage between the phase 2 and 3. You always have to find the voltage on the other two lines. The problem is the direction. So here, if you have V1, maybe it's better if I draw it in a bigger dimension. V1, I1. Then you need a voltage which is orthogonal. So should be in this direction, okay? So that here you have pi half minus phi, okay? That's why we use V23. This is natural. The third is also natural because it's still pointing up. For some reasons, I see students forgetting or making the connection wrong in this middle case. They know they have to go for the other two terminals, but they connect it vice versa. They connect it with the positive here. One, two, three. And they measure, in this case, V1, 3, which is the opposite of V31, okay? I don't know, for some reasons they don't like if the voltage points down. But always remember that you need a voltage orthogonal with this direction. So in this case, you have V2 is here, I2 is here. You need a voltage V31 to be orthogonal, like with this direction, to have pi half minus phi, okay? So V31, not V13, okay? Fine. So if you don't remember the direction, you can memorize it, but it's always better just to draw the vectors and try to find pi half minus phi, okay? It's very simple. Just avoid to memorize things, just try to do it. Just maybe draw the diagram of the vectors and it's easier to retrieve the direction, okay? Now, how do we measure the power? How do we create this wattmeter? So far, I just told you how you connect it, okay? Now we see how, in practice, we measure this power. I will start actually from here. I have only 10 minutes left, so I will start from this wattmeter, which is giving me the opportunity to give you an interesting question. A very basic method to measure the power is simply to digitize both the voltage and the current. In case of the voltage, you maybe decrease it because it's too large. You don't want to measure it. Sorry. You don't want to measure it directly, so you reduce it, I don't know, by 50 times, 100 times. With the voltage transformer, and then you sample it. The same for the current. For the current, you might consider transforming it into a voltage before converting it into samples. Okay? So you transform the current into the voltage, and then you sample it. Once you have the samples, you can simply multiply them and get the power, right? Shouldn't be this difficult. I told you in the very first lecture that once you sample the voltage and you take a number of samples which respects the sampling theory, in those samples you have all the information of the data, of the original data. There is no piece of information missing. For instance, for a sine, I told you it's sufficient to measure 3 points per period, right? Then, of course, there is also this point which belongs to the following period. Okay. If you have 3 samples per period, you get all the information of the voltage, right? Is that correct? Remember, be careful. I said it's not when you arrive at the end and you sample all your data and you reconstruct the signal, you don't make interpolation. Because once you have these 3 points, you have all the data, all the equations which give you the unknowns of the system. Therefore, you know everything about the voltage. Everything. Nothing is missing. If you know everything, you know also the power it can give you if you have another signal which represents, for instance, the current. Okay? Let me draw it here. This is the voltage. This is the current. I take, again, the samples here. Fine. So, I take 3 points for the voltage. I take 3 points of the current. They are both sines. I know everything about the voltage because I've taken points enough to know everything about the voltage, right? I know everything, but sorry. I know everything about the current. The sampling theorem tells me that if I have these 3 points, I know everything about the current. Fine. Now, if you want the power, you have to multiply these two. Sorry, I do apologize. You have to multiply these values, right? And what do we obtain? Well, the power, as we saw, will be something like this, right? Now, the drawing is not really precise. Let me draw the drawing again. Okay? So this is the power. 0 times 0, you're here. These 2 points will give you this point, right? Now, these 2 points, again, they should be in the same moment. They give this point, right? I apologize if the lines are not perfectly straight. Forgive me. Now, again, we have 3 points, but the frequency now is twice the original frequency. If this is 50 Hertz, as we have seen at the beginning of today's lecture, this will be 100 Hertz, right? If this is 20 milliseconds, this will be 10 milliseconds, okay? It means that now we take 3 points over 2 periods. And this is not enough. In the same period of 20 milliseconds, we have a second harmonic. So we should take in those 20 milliseconds not 3 samples, but guess what? 5. Because here, in the first case, we have the number of samples is 2n plus 1. N is the first harmonic. And it's also the highest order harmonic. In this case, we have n, which is given by uppercase n to uppercase n plus 1. But the highest level of the harmonic is the second. Right? So, here I would need 2 times 2 plus 1, 5 samples in those 20 milliseconds, right? We doubled the frequency. The frequency, the order of the highest harmonic is 2, is not 1 anymore, and therefore we need 5 samples per period, or per period in this case of 20 milliseconds. But we have only 3. So these 3 points in 20 milliseconds are not enough. I would need 5. So, what does it mean? It means that I have to sample with faster analog to digital converter. My sampling frequency should be larger in order to get 5 samples per period instead of 3. If I want to use the data of the voltage and the current to get the power. Right? So instead of using an analog to digital converter which gives you 3 samples per period of 20 milliseconds, you need to use an analog to digital converter with larger sampling frequency. Right? No? Not at all. And you know why? Because these 3 points here of the voltage and these 3 points of the current have all the information about the voltage of the current. And if you have all the information of the voltage and of the current, then you necessarily have all the information about the power. The point is that by moving from these 3 points of the voltage and 3 points of the current to the 3 points of the power, you lose some information. This method is wrong. Because on the way of from these 6 samples to these 3 samples, you lose some information. This method is wrong. You must find another method. The information is here. And here you have lost it. You must find a way smarter method to get all the information of the voltage and all the information of the current to the power in such a way that you don't lose any piece of information, and you can actually have 5 points per period of 20 milliseconds. This is a very interesting task. I give it to you. It's not easy to solve it. Accidentally, it is explained in my book, but my book is written in Italian, so I'm not sure how many of you can read it. So you cannot cheat and go to read the solution of my book. But because it's not simple, I'm going to give 5 points for that. So if you come with a solution to this problem, you get 5 extra points, which is half a mark. It's quite a lot, okay? That's all for everything. Tomorrow we will continue the 3rd lecture. And if you have any question, just please give me your questions. Otherwise, I wish you a nice afternoon. Let's see if there is any question. As usual, of course, I will add to MS Teams the text of the assignment, right? So if you missed the explanation, you can read it back. Yes, meanwhile, I've already answered you. Yes, I will put the assignment so that you can see the question. Anything else? Any other question? If not, yes. The problem is that there is a delay in YouTube. There is about 10-15 seconds delay, so it takes some time before you hear what I say. Okay, so if there are no other questions, enjoy your afternoon. It seems, no, yeah. So somebody is asking why in the box for the current there is current and the voltage. This box means that you transform something, okay? So when you see this box here, it means that you enter with the current, okay? Here you connect the current and you transform it to a voltage which is proportional to the current, okay? Because, as a matter of fact, the analog to digital converter measures a voltage, okay? So you have to take the current, you transform it into a voltage, and then you convert the voltage. Always, it's like that. You don't measure directly a current. It could be, for instance, a resistor, okay? So you inject, sorry, you inject the current into a resistor and you measure the voltage drop on the resistor. Or, for instance, you can use a current to voltage converter based on operation amplifier, okay? We will see the difference between them and when to use one and when to use the other, okay? Okay, I think I hope I have answered your question. Okay. If you have any other question, just contact me on email or on MS Teams. Have a nice afternoon.